Okay, problems, more problems. So let's do this one. This is a fun one. We have this inclined plane here. Angle is beta, there is gravity, and there is the usual uniform disk that comes down the incline. Let's call this point of contact P. Center is O. And the incline is frictionless up to a certain point, and then there is actually friction here. So there is a sudden transition to a friction zone, which is given by mu. So what kind of friction is this? If I'm giving you mu, which kind is it?
Coulomb friction?
Coulomb? Is that the one we called Coulomb friction?
I think so.
Yep.
Because viscous has
Viscous as the velocity, right? Okay. So the things you're given is the disk starts at rest. It's a rigid body. So what this means, you tell me in a second what this means. I'm going to skip the initial steps. I'm just going to give you the coordinate system here right away, because at this point, if you don't know how to do that, well, it's too late. Ex, Ey, Ez is fixed to the ground, which is G, and it's an inertial reference frame. Ex goes down the incline, Ey is perpendicular to the incline, Ez goes into the page, and then this object here, which is has a radius little r, its configuration is given through an angle theta. And so this is also another reference frame, which I'm going to call A. And attached to it, we have this coordinate system, Ex, Ey, Ez. So what I'm doing here, I'm choosing Ex radially from point O to some point on the edge of the disk. Ez is as big Ez, so little ez and big Ez are the same thing. And then Ey comes as the cross product. Okay. Now, this is a frictionless portion here. This object starts at rest. The questions are, one, I don't know what the questions are actually, velocity and angular velocity, velocity of center of mass, and angular velocity of the body, which I called A, right? So this is fixed in A, which is the disk. So omega Ag, basically at D, when you reach this friction portion here. And then the second one is distance, the disk runs when roll starts. So for once, we're going to do something with the equations of motion that we get. So these will go beyond finding the equations of motion, is actually using them. But I'm going to try to be a little quicker than usual because they're not that difficult. What we need to understand is, if I'm telling you that a rigid body is at rest, what does that mean? Two different things. What does it mean?
It means the velocity is, the initial velocity is 0.
Of what? It's a rigid body, uniform rigid body.
The velocity of OSC from G is 0.
The velocity of center of mass, with respect to G, at t equals 0 is 0. What else? A rigid body rotates and translates. The angular velocity of A with respect to G at t equals 0 is 0. We know that. Now, I'm assuming we all can imagine, but we're going to show it, that as this starts moving down the incline, because there is gravity, it's probably not going to roll. We'll see it, which means it's sliding. And then when it hits this surface, we'll start having Coulomb friction that will eventually reduce the relative velocity between the 2 points here that are touching each other, the point of contact, until that goes to 0. That's when you have roll. You don't want relative velocity at the point of contact between the point P on G and A if you have roll, right? So this is going to you can imagine this just going down, and then at some point it starts having friction here, so eventually we'll start accumulating some angular velocity until the point of contact has the same velocity on the disk of the point of contact on the ground, so there is no relative velocity. So that's the big picture. That's what you need to think about. But so in general, when I start looking at this, I see an angle theta, so that's a parameter that I'm going to use probably. But how many degrees of freedom do I really have? I know we've seen problems with rolling, and that comes down to having 1 degree of freedom in a plane. Does this have 1 degree of freedom if I have no friction here?
You have 2 up until you get to the friction part.
Well, I would say that you keep having 2 until you have roll. Roll is a kinematic condition that will remove a degree of freedom, but until you get there, you have 2, because the center of mass O can only move in a line, which is this dx. We'll call that x probably, right? We're gonna start counting x from, so the origin for the ground fixed reference frame coordinate system. I'm sorry, it's going to be O at time 0. I'm just not spending time on this. So I will start counting x from there. The origin for the other coordinate system is O itself at any time, of course. So unless you have roll or something else, this object can translate and rotate, and those 2 things are independent, right? Roll makes them dependent from each other. They're not, so it goes down to 1 degree of freedom. But for now, I don't have roll, so I treat them independently. So these are the 2 questions here. We've done the reference frames, so we've done the coordinate systems. We are looking at finding the equations of motion to respond to these 2 questions, right? I have the initial conditions. I know what I want at a given distance from the initial state. I need to find the equations of motion. So that's a rigid body. So that tells me that the first law tells me that summation of all forces is m acceleration of the center of mass. Please tell me right away what is the acceleration of the center of mass. This is an A. What is the acceleration of the center of mass, which is point O? I have x and theta as variables. Those are my parameters through which I'm going to solve the problem. I'm going to find the equations of motion in terms of x and theta. What can that point do? It's only moving on a straight line, right? We've seen this several times. It's x double dot.
I mean, mx double dot.
Yeah, that's it. So no surprise there. And what is f? So f, free body diagram. We are looking, so this is, if you want, phase 1. We call this portion here phase 1 here. There's no friction, and then we'll deal with phase 2 where things change. But for phase 1, I have the gravity force here. And then since that object, that the ground is frictionless, I have some reaction here, right? That goes through point O. Okay, so my F is what? Is mg. Let's project this thing right away. How do you project g? This is beta, the beta angle of the plane. Let's use the ground fixed coordinate system.
Yeah, g is.
You guys tell me. Do you like this? You guys tell me.
Yeah, that's right. Yeah.
Is that correct?
Yeah.
It looks correct. Okay, plus, is it a plus? They're all pluses, yes. Okay, this noise is really pleasant, by the way. And then n is, what is n? How do you want to write n? Let's go down here. What is n? N is easy, right? N EY, correct? So this is equal to mx double dot EX. So this breaks down into 2 equations. I have that mg cosine of beta is n, right? I only see EY and EY here. Actually, this is with a minus. And then I have on EX, m g sine of beta, beta equals to m x double dot. That's a simple problem. Something going down the incline, really, for the first equation. There's nothing special here. Okay, so that would be the first equation. It's first Euler's law. So let's, as you can see here, I'm kind of compressing kinetics and kinematics all together. I'm just going a little faster than I should, but at this point I hope it's clear that by telling you that this is the acceleration of center of mass, I have done kinematics as well. So for the second one, well, let's go a little slower. What do I need to compute? First, the kinematics part, which is also very easy in this problem, but what do I need to do? Kinematics is acceleration of center of mass. So that was really easy. We've done it right there. Second part of kinematics for a rigid body is h bar, right? You always do this. There's no escape. What is h bar? You start from the definition. And let me make a comment here. So this is the inertia tensor with respect to the center of mass for the body A, dotted with omega a g. Now, some people during the first test had issues with basically mixing up letters, and so after calling, like in this case, after calling the disk the rigid body disk A, reference frame A, instead of being consistent and using A here, they will say R, right? Because that's what I've used for rigid body. And after having called the ground G, they will say N, because that's what I've done for inertia reference frame. And then after having called the coordinate system, which is fixed in A, Ex, Ey, Ez, they would express this saying E, I, R bar, ER equal cross ER plus I theta bar, etc., etc. Now, is this wrong? Yes, it is wrong. It is wrong because you decided to call those vectors that way. And now what you're doing here, you're just emulating by memory what I have done somewhere else for another problem. You're not being consistent. You're being a messy engineer. If I were your boss, I would fire you right away. Think about your exam as a report you give to your boss in a certain way. Something like this is crazy. You're just being inconsistent completely. And you keep doing these nonsense changes of terminology during the problem. Of course, I have to give up correcting the problem because I don't understand where you're going. You start calling that A reference frame, and then it becomes a point, and then you call G a reference frame, and then it becomes something else. There's no way that can be counted as a well-solved problem because you are messing up completely the problem. You're not being consistent with yourself, and that's really bad. So just a piece of advice, because I've seen it, and you're going to be penalized if you do it, because I can't understand what you're doing. If you start from that, and then you start introducing vectors that don't exist in your sketch, I don't know what to do with them. And I'm not gonna, unfortunately, my job is not reading your minds, so I'm not gonna try to guess what you wanted to tell me or do. I'm going to read what is on paper. So be consistent, that's a piece of advice. Okay, so if you want to be consistent, that's A, and that's G, that's fine. Then tensor of inertia I with respect to the center of mass. In general, since that's a principal axis of inertia coordinate system, because the z-axis is an axis of symmetry, and then x and y are also in the plane. So that would be I bar xx ex circle cross ex plus I bar y ey circle cross ey plus I zz bar ez circle cross ez dotted with what is the angular velocity of A with respect to G is theta dot ez. That's why I picked my vectors going into the board, so it's consistent with the sign of theta. And as you've seen before, the only term that survives is this when you do these products. tensor products. So you get IZZ bar, and let me just call IZZ bar, and this is in tables in books, and I refuse to memorize it, so I'm just going to call it I. To make my life easier, I call it I, and so this is my H bar. Whatever that I is, I think it's mr squared over 2 for a uniform disk. I don't really care. It's a constant. So this is fine. If you simplify your life because it's easier to keep writing things, you can do it, but you have to tell me. Okay? Definitely you don't want to change the name of the basis along the way. Why would you do that? Okay, so that's H bar. And so the second law, well, tells me something that, for example, d dt in G of H bar G is equal to the moment of all the forces with respect to the center of mass, if I pick the center of mass as my point. Remember, you're free to pick whatever you want. Now, is that a good point? This was the free body diagram, right? Gravity acts this way. This is the center of mass. Oh, the reaction I have is pointing that way. So if I pick that point, all forces actually go away. They have no moment, right? Yeah. So the ddt in G of that is simply I theta double dot Ez equals 0. Why can I do this? You really have to think about what you do. Every single step. If you can't justify it, you just need to stop. Why did I take the derivative of that like this? This is rate of change with respect to G.
Because small Ez is equal.
Because Ez is fixed in the ground. Doesn't change in the ground, right? Yeah, it's equal to big Z. It's, yeah, that's it. Yeah, that's a basic question, but people get stuck there. So you need to know. Well, that tells me that if I'm starting at 0 angular velocity, it's not changing, because theta double dot is you can see this as the omega dot. I can say this is not a vector, right? Since the motion is only about, the rotation is about the z-axis only, I can call that just omega as a scalar. So this is 0. So omega is not changing. Do we agree? Yes? No? And it makes sense. There's no forces that create any moment with respect to the center of mass. So that object starts at rest, it just slides down. Doesn't change orientation in a perfect world, of course. Okay. And so in the first segment, frictionless segment, those are my equations of motion. Well, this is another one. Or if you want, theta is constant. Theta remains whatever it is as well. Yes?
That's just because it's frictionless now, right?
Yes.
Friction, then down.
That will change. They will do this again for the second phase where the free body diagram changes, because I'm going to have an additional force now.
You can have a moment.
Right.
Okay.
Correct. Yep. We're going to have to express that force, the Coulomb friction first, and then find its moment. That is correct. So, but now I can answer this because I have the equation of motion for phase 1. Actually, you know, these are questions 1 or 2, but they really belong to the different phases, so I can do this. I have everything I need for phase 1. What is the velocity of the center of mass when I hit D? So what is the equation that... So this really doesn't tell me much. This tells me, well, it tells me that this will be 0. Second law of Euler tells me that the angular velocity of A with respect to G at x equals D is 0. Okay, so you've answered a piece of that. It's not going to change. Starts at rest, just slides down, doesn't change orientation. So I'm done with this. How about this? Which of the equations that I have here I can use?
The mx double dot.
Right, that's a nice equation, right? Remove the mass, x double dot is equal to g sine of beta. This is one of the simplest differential equations that you can find. It's something double dot equals a constant. Now, the question is, what is, and the velocity is x dot, right? Do we agree that the magnitude of velocity is x dot? The velocity of center of mass right? So if you find these, when so the other piece that I need to find is x dot when x equals d. I don't know this, but I can get it from this equation. And for once, we're going to solve the differential equation given the initial conditions, something that we haven't done so far. And it's really not the point of this class, but for something this easy, you should be able to do it. So how do you want to do it? That's one way. Integrating twice gives me a function of time for the x. That's fine. You can do it. Then you have to substitute back and forth. There is another way. X double dot is what? It's called separation of variables, right? It's dx dot in dt. That's what x double dot is. And how about I do this? Divide and multiply times dx. Okay. I can do that, right? Then what is dx in dt is again x dot. So I have an x dot dx equals g, I'm sorry. Yeah, dx, yeah, dx dot, yeah. G sine beta dx. Is this step clear? Yeah. Separation of variables. Calculus is something that I have to give for granted. And it doesn't mean that I remember how to solve every differential equation. I just know where the book is to do so. Okay, so now I can integrate these and actually get a relationship between directly x dot and x, which is what I want. I don't really care about the function of time that gives me x. Okay, so let me just save a few things that I need here. Let me write them down here, actually, so I can erase that. So the equations that we have found are m minus mg cosine of beta equals n, and then that one, and g and then that's fine. Okay, so we move here. If I integrate the left-hand side, I have x. What do I have? Between time 0, or in this case, between x dot at time 0 and x dot at d, what do I get?
What?
This. I'm integrating the left-hand side of x dot dx dot.
You're going to get 1/2 x dot squared at t equals d minus.
Right? In d.
Yeah, minus.
Let me be a little more thorough here. This is what I should write.
Yeah. Minus x dot squared at x equals 0, which is 0.
Yeah, this is 0. And this is equal to g sine beta. Okay, that's x
Times d minus g sine beta times 0. So you start counting from the origin.
x. Yeah, if I start counting from there, I know that this is d actually, right? This is d minus 0. That's it. That's what I have here. Okay, so my velocity squared at the point of interest is going to be equal to 2g sine beta d, and then I take the square root, and that gives me what I want. Okay. So that object starts at rest, does not develop any angular velocity, remains 0, but the center of mass is, of course, accelerating with that equation down there. And its velocity is going to be this square root of 2g sine beta d when we start entering the second portion with friction.
And the reason we know it's positive is because it's going in
Yeah.
the
Yep.
right?
Yep.
The fact that it's squared could mean that it could have been
Yep.
either.
Yeah. And if you look at these, x double dot is also positive, so it needs to increase. X dot has to increase from 0. It starts at 0, so increasing means that goes to positive values. Okay, let me just write it here. X dot at x equals d is that square root 2g sine beta d. Now please understand that these, and then theta dot at, theta dot at x equals d is 0. And if you want to put units here, this is meters per second, and this is radians per second, right? If you really want to. So this is answer to question 1. And those are your new initial conditions. Now I'm going to start phase 2. Those are my new initial conditions. So forget about this. Now this is my start point, and I have the disk here, right? Touching here. So we can forget about these initial conditions here. I don't need them anymore. OK. Any questions on this portion? That wasn't that bad, right? The new element is, wow, we can really do something with these equations of motion that we've been computing, right? It's not too bad. We can use them. So I need to answer this. What is the distance when the roll starts? Well, let's figure out what's going on first. When I hit that, that portion, my kinematics is the same. Acceleration of center of mass will still be given as x double dot ex. The h bar will still be, so acceleration of center of mass with respect to g is x double dot ex. And h bar with respect to g, I think it was I. Is this what I had? They don't change. Kinematics is the geometry of motion. That's not going to change. It doesn't matter what forces you have. The free body diagram does change. So the free body diagram now has one more force. OK? I have mg still here. I have my normal reaction still here. And then I have my Coulomb friction here, force of friction. And now we need to open the book and find the model for that force, because that's the only thing that we have added to the mix that we didn't have before. What is this? What is the expression for Coulomb friction? I don't care you about memorizing this. You just need to know what it is. Right? I think it was something like this. Is the one that for years we've seen is the pressure normal to the plane times the constant. And there was no VREL. But this is a vector. There must be a VREL. So now it is for me to figure out all these components. This is a constant. It's given. What is the norm of n? Now, I have to rewrite first Euler's law. But my guess is that this was on the y direction, right? This is the projection of the Euler's law in the y direction. This is in the x direction for the phase 1. When I go into phase 2, I'm adding a force in the x direction, but I'm not doing any changes on the y. So that's n, actually. So I know this. This is mg cosine of beta. Do we see what's going on here? I haven't read. So my new statement of the first law is going to be, again, mg plus n. I had this before. The only thing that I've added is f sub f. And this is equal to mx double dot ex. So if I project these in the x direction, I get something new because there is f sub f. But in the y direction, this doesn't project, doesn't have any contribution. So I still get the first equation down there, this one. And so if you take the norm of that, that's mg cosine of beta. That's nice. I have one component already. I have to figure out the relative velocity. What is the definition of relative velocity between two surfaces? You go back to the book again. You don't guess. Because we've done it, we defined it, we used it several times. It has to do with the point P, which is the point of contact, right? It is the velocity of point P as part of A seen by any reference frame. It doesn't matter. In fact, this doesn't have a reference frame. Remember? It's independent of the reference frame, and we demonstrated that.
You say that's seen by A again.
I see the ground. I see the ground for now, just because then I have to do VP now belonging to the ground as seen by the same reference frame, and this is obviously 0. So this is only the velocity of P on the disk, right? OK. Now what is this? I don't know.
Transport theorem.
Transport theorem with what? So this is O, and this is P. And this is a rigid body.
Okay, so P is not moving relative to A. If you're sitting on A.
Of course, no, it's a rigid body. No point moves with respect to the rigid body itself, if it's on the rigid body. But I want it with respect to the ground. When you see 2 points on a rigid body, you should always think about just a couple of things. There are 2 things that we've done for kinematics of rigid bodies before we actually added the angular momentum. 2 additional things. If I pick any 2 points on a rigid body, Q and Q prime, velocity of Q minus velocity of Q prime, if they are part of the same rigid body, is equal to omega rigid body with respect to G cross with RQ minus RQ prime. Remember this? And then there was something longer for the accelerations. I don't really need that here. So what can I do? I have the velocity of O. I do. It's x dot EX. So how about I use that information? So in here, I'm going to do the following. I'm going to do VP with respect to the ground minus VO with respect to the ground. I know this. It's the angular velocity of A. See, it's not called R. I called it A. It's the angular velocity of A with respect to G. So yeah, it looks like the transport theorem, but it's not really. What do I have here? I have RP, RP, and RO. Okay? So this is telling me that VP, let me just write it this way. VP in G is the velocity of the center of mass, the x dot EX, plus theta dot EZ cross with what? Yep.
Or wait, no, it's EX.
Not EX. Sorry. Yeah, it's not. It's EY. It's the vector that is going this way or that way.
Yeah, my bad.
Is it going this way or that way? From O to P or from P to O? These are difficult questions, I know. REY?
Yeah, that's correct.
Yeah, so, okay. Even though these seem to belong to different families, they're really not, because big EZ and little EZ are the same thing. So how about I do this? That makes my life easier. What is big EZ crossed with EY? It's minus EX. So this ends up being x dot minus R theta dot EX. And that is actually my relative velocity for what I observed there, right? Agree? Disagree? Comments, concerns? So that's my VREL. So I can definitely stick that in here. But then I have to figure out the magnitude of it. Can I erase this? Probably. So this is mg cosine beta. Let me just rewrite that. So my force of friction is minus mu mg cosine of beta. This is taking care of the magnitude of n. And then I have, at the numerator, I have x dot minus r theta dot ex. And down here, I have the norm of the safe vector, which ends up being the absolute value of x dot minus r theta dot, right? Is that plus or minus? So when I remove the absolute value, and of course I will simplify these, I will end up with a plus ex or a minus ex. So when I hit phase 2, this is what you should go back and think what has happened. This thing has started going down, no omega, remains at 0, accumulates an x dot, and the x dot, when you reach this point, is this square root. It's a positive value. So at x equal to, when this starts, when the friction kicks in, the x dot is positive.
Yeah.
The theta dot is 0. So this thing is positive. The whole thing is positive when you start phase 2. My goal will be reaching the point where the velocity, the relative velocity goes to 0. That's roll, right?
Yeah.
That is what roll means. You don't want, so if the relative velocity is defined as we did before, relative velocity is the difference between velocity of point P seen belonging to A with respect to the ground minus the velocity of point P seen belonging to the ground with respect to the ground. Well, guess what? This needs to be 0 because this is the definition of roll. Remember?
Yeah.
That's exactly what roll means. So in other words, you want VREL to go to 0. So this VREL, in terms of sign, the sign of the norm of its magnitude, starts at a positive value, x dot equals that, because theta dot is 0. And it will have to eventually go to 0. That's when roll starts. So it's a function that goes from a positive value to a 0 value. Do you think this function will go up and down? This is going to be positive until roll starts. Right? Another way to see it is yeah, that's it. That's the way to see it, actually. Does it make sense? So I can remove the absolute value and say that this is, in the end, minus mu mg cosine of beta Ex. Okay, so I can substitute in there if you want. Yeah, I think you should do it. Do I need all these? Let me just write that the relative velocity, just to remind me, is x dot minus r theta dot Ex. That's what I have. So if I go back to my Euler's laws now, I have, well, again, the y one I told you doesn't really change. The second one on the x, I have mg sine of beta minus on Ex, right? Force of friction equals mx double dot Ex. So in other words, you have another equation with everything known, mx double dot, well, simplify the mass. X double dot is going to be equal to mg sine of beta minus mu, yeah, I said I simplified this, minus mu g cosine of beta. That's it. That's an equation I can solve with that initial condition. Reset time to be 0 when you start phase 2 if you want. You can do that, and this will be your new initial condition. Okay? You can say that x starts again here. So you can call this x equals 0 and this is your initial velocity, or no, you don't really need to do that. You can just keep the x to be d. So the initial condition for position is d, the initial condition for velocity is that square root, but you can restart time. Okay, that is my first law. Gives me a nice equation that I can integrate in time. The second one is still the same. d dt in g of h bar g is equal to m bar. And I think I still want to use the center of mass. I added one force, but this is a known force. The other two were already giving me 0 moment. So that's perfectly fine. So this translates into I theta. I made a mistake here, right? Dimensional mistake. H bar is I theta dot, not theta double dot. The theta double dot shows up when you do the derivative. Ez. So that's the first term. Okay, what do I have here? The moment with respect to the center of mass, so with respect to the center of the disk, of this force F sub F, which I perfectly know now, it's pointing negative in the negative direction of x. So I am computing the moment of this force with respect to O. So that is R Ey cross with F sub F, which is minus mu mg cosine of beta Ex. Okay? Z. What is Ey cross with Ex? Minus Ez. So there's a minus here that goes away. I have mu r m g cosine beta E z. Good thing they happen to be in the same direction, otherwise that would have been a mistake. Big Ez, little ez are the same vector. So this is my final equation of motion for the rotation. So if you want, you can divide by I, and that gives you the other equation for the evolution of theta. What is the initial condition for this? You can say theta was 0. Theta dot was 0 because that's what I have when I hit the friction phase. So you have two equations that you can very easy differential equations. Again, it's something double dot equals a constant. They're nothing special. You integrate them once, you get x dot, theta dot, and you impose the condition that this needs to be 0. Right? What are you going to solve for? The question was how much distance you run before roll starts. And we agree that roll starts when this goes to 0, right?
Yeah.
So how would you solve this again? Do you want to integrate it twice? Do you want to do separation of variables? What do you want to do? You need to find a distance, like before. So you can find both in terms of thinking.
In terms of everything you have in here.
Yeah.
So
You can integrate twice.
From that position to some distance d1. Both of them. And
Or
then
if
integrate this equation and then solve for it.
Yeah.
And
Yeah, this becomes a little.
It's because a function of
Let me.
r and all
I
that
don't think we need this anymore. So let me see the first one for a second. The first one again has this initial condition now. So I'm talking about this equation. If I just integrate with time, which is probably what I should do, because I get the time when roll starts, and then once I have these integrated twice, I can stick in the time. If I integrate it twice, I get that x dot as a function of time is equal to what? Is that constant t plus this. Right? Isn't that what I have? Because I do know that at time 0, I have restarted time when I start the friction section. This is my initial velocity. So when I integrate once, that's what I get.
Why can't we do it with respect to distance though?
You want to do it with respect to distance? We can do it with respect to distance. I don't know if I'm just concerned about the other one. Well, let's do it with respect to distance. What do you get respect to distance? What do you get? Like before, right?
Yeah.
I have an x dot squared over 2 minus this squared right over 2, because that would be my initial condition, is equal to this ugly constant here, times x minus d. Is that what I should get? I think so. And so you can bring everything on that side and get a function of x dot in terms of distance, x. So that's fine. You can in this way you find a function x dot is a function of x, whatever that is. But the problem is the second one. I don't think you can do the same. So that is the problem. I don't know if that's of use now in this case. That's why I was going for the double integration and actually finding an expression of time. Yeah. Yeah, I don't think. I mean, you can do the same thing with this equation down here and find the function of a theta dot function of theta. So you can find this theta dot as a function of the angle by doing the same thing here. But so once you have those two, you plug it in here, you can't really solve for one thing. Because the problem, what is happening is, until roll starts, x and theta are doing whatever they want. They are independent. When roll hits, then they really collapse into one parameter. They are related to each other, right? But until the point, they're not. So if I find these two expressions that I told you, then I substitute in here, I get an equation that tells me, okay, the function x dot of x, which is the distance, minus the function theta dot of time times r needs to be 0. And these are two different things. They're not related to each other. And I want these when roll starts. So this doesn't help me to solving the problem. So I think in this case, you're better off by integrating this twice, find x as a function of time, this twice, find theta as a function of time, well, and x dot and r dot and theta dot. So you would, yeah. You integrate it once, you find it as a function of time, stick it in here, you integrate this once, function of time. So you basically substitute there and find t when roll starts. Then if you want the distance, you have to integrate this twice and stick that t in there. And this is where the calculation gets ugly. I mean, ugly. It's doable. We have done it there. That's the x dot function of time. The theta dot function of time is even simpler, right? Theta dot of time, if I look at this equation here, is whatever the constant is, mu r m g cosine of beta over I t. And all initial conditions for these are 0. I assume that theta was 0 at the beginning. It stayed 0 until I reached the friction portion. There was no theta dot because it's 0. So this is really my function of time for theta dot. So I do have these two functions of t. You can multiply this by r, substitute there, find t, solve for t. And then if you really want the distance, you have to integrate that twice to know how much distance you have run until the point of rolling. So if you want the other piece that you would need is integrating this twice, which gives you x of t, which is g sine of beta minus mu g cosine of beta over 2 t squared plus 2g d sine of beta t plus d, which is my initial condition for x. And so once you have t that you found from imposing this to be 0, you can substitute there. It's going to be a pretty nasty expression, but
it's going to be like minus the square root of that.
Yeah. It's going to be fun, but nothing special really. And solving this problem was not that bad, right? Now, since we're out of time, how about, here's another homework for you, try to solve with Lagrange's equations. Comment, the first phase will be really a piece of cake. The second also will not be that difficult, but now this force of friction, which is Coulomb friction, is not a static friction. This cannot go away in your generalized force. It's not a constraint force, exactly. It does have virtual work. Think about this problem, the incline. So in this, when we define virtual works, we said constraints can move with time, but we freeze them. Well, in this case, it is frozen already. It's not really moving. I'm telling you that this is an inertial reference frame. So in this case, virtual work or real work, there's really no difference. So this point is moving, and this force does make work. This point doesn't have a zero velocity until roll starts. Then it becomes a constrained force, but it's not until that point. So try to do it with Lagrange's equations as an exercise. So you guys need to tell me if you want to have lectures on Monday, because Monday what I will do is probably look at some of the stuff that we've done and how it's used for dynamics of orientation dynamics of spacecraft. So just to show you one more application, but only if you want to. Okay?